Watch Derek Mack. It says
Her
live in
boyfriend.
30 minutes.
Yeah, that I don't know what
I
that's
hated
about.
that so much.
Cheater. Yeah, no, I didn't really just.
All right, Chatty
You saw, remember
Cathy's.
that one we got online?
Yeah.
Oh my
Is that
God.
the one?
Yeah.
So today we're going to learn about proof by contradiction. We talked about it a little bit yesterday, but I wanted to kind of cement this idea. So here's the concept. What you're going to do is you're going to, instead of trying to just prove something outright, you're going to assume the opposite of that, right? So they're going to tell you that these two numbers, right, prove two positive integers always have a positive sum. So think of two numbers, right, no fractions allowed. Two numbers that are positive, right? When you add them together, you get a positive answer, right? Always. Now we're going to prove that that's true. And that's really hard to prove because you have to prove for all different numbers, right? So we're going to use variables to do it. Also, we're going to assume the opposite of that. We're going to assume that it's not going to give you a positive answer. And we're going to show that that's absurd, right? That it would be ridiculous to have two positive numbers added together to get a negative number, right? There's no way that's going to happen. So we're going to assume it's true and then show why that would be stupid, right? It would break math, all this stuff. We're going to show that. And once we've thoroughly shown that it is absurd, that it's a contradiction, right? Then we're going to say, because this is so absurd, there's no way it can be true, which means the opposite must be true, which means they must add up to a positive number. And that's the power of proof by contradiction. It takes a really ridiculous argument and shows how ridiculous it is, to the point where you go, then the opposite must be true, and then you win. That's the idea. This is really good in debate tactics, right? You say, for a second, I will assume my opponent is telling the truth, and their logic holds out, and then you'll say, and here's, if that were true, all these things would be true, and these things are a bunch of BS, so you know what they're saying is dumb, right? So that's what we're going to do with this. So here we go. It says, prove two positive integers always have a positive sum. First thing you should do, if you had algebra with me, you would know that this is actually the wrong symbol. You want n sub 1, not n sub 0.
What does that even mean?
Great question. So remember at the beginning of the year, dang, she thick, right? Thick letters stand for sets, okay? This is the natural number set. And when it has a 1 down here, it means natural number starting at 1, okay? If it had a 0, we call it the whole number set or natural number starting at 0. So any number like 1, 2, 3, 4, any of the numbers you count your sheep with are what we're talking about. So this is saying that E right there means exists in. So it's saying A and B exist in this set. They're natural numbers is what I'm saying. A and B are natural numbers, so the ones you count your sheep with, right? So given that A and B are natural numbers, positive whole numbers, right? Then when I add them together, I should get something greater than 0, otherwise known as positive, right? So we're going to prove that true. And you know this to be true, right? Pick 3 and 4, right? What do they end up with? 7. Is it positive? Yes, right? Any two numbers you choose that are natural numbers starting at 1, right, will add up to a positive thing. But we're going to assume the opposite to prove this by contradiction. So we're going to say assume A plus B. What's the opposite of greater than 0? So we're going to assume that A plus B is less than 0. And otherwise known as A plus B gets us a negative number, right? Anything less than 0 is negative. Now, I'm going to show you why this is absurd, okay? Why this cannot be true. And then once we've proven that this can't be true, then the opposite must be true, and we win. So I'm going to say, just by algebra, right, I'm going to move over B by the subtraction property. I subtract B from both sides. What's 0 minus B? Think about it. What's 0 minus B? Negative B. Now, I'm going to make some notes, which you don't need for your proof, because it's already implied. But you're going to tell me why this has to be ridiculous. Now, what happens when you negate a positive number? What happens? It becomes negative. So tell me why this statement is ridiculous. Think about what it means. Raise your hand if you think you have an idea. Bailey.
Because B is negative and it says that A is less than.
Yeah. We can never have a positive number that's less than a negative, right? That doesn't make sense. Name me a positive number that's less than a negative number. Negatives are always less. So this can't be true. So what we say is contradiction. Now there are lots of different things you can say here. You can do contradiction. You can write absurd. You can even put an exclamation point if you want. You can write an interrobang. I've got your interest, right? Interrobang, interrogative, like interrogative sentence means question mark, and then the bang is the exclamation. So interrobang is what we call that. It is an actual punctuation.
Is this true or are you making this up? Is that what we call it or what you?
No, it's what it's actually called. Yeah.
So if I set that in my English class.
Yeah, they know what it is. Interrobang. At least I would hope they would. You can also do this cool lightning bolt. Wait, how do I do it? Is it like that?
You can say any 4 of those.
How do I do the lightning bolt? I forgot.
Right.
Is it like that? No. Oh, it's like that. It's this one. It's this one. That's the one. Sorry. I made a rest music. Sorry.
What?
None of these.
I'm lost.
That's a musical rest. So this also means contradiction. It's a cool lightning bolt symbol, right? Think Harry Potter with the dot at the bottom. Harry Potter with acne, right? You can also write this symbol, which is 2 arrows pointing at each other. It kind of looks like 2 smiley faces looking at each other. Right? They're bold arrows. You have to use bold arrows in math.
Yeah, I don't think I'm gonna make the bring. I'm gonna slide out in the snow and get it.
Or you can do this, X with 4 dots. Any of those mean contradiction. Okay? So we have a contradiction. Therefore, right, that's what the 3 dots mean. Our assumption
Therefore,
was false.
Wait, what are those 2? The X with the dots and the
That's contradiction. All these mean contradiction. All of these mean the same thing. You can use any of those. You'll probably see me use this the most, or this. I think lightning bolt's super cool. Sometimes when I'm feeling funny, I'll use absurd. Absurd! So our assumption was false. Therefore, A plus B is greater than 0. And we're done. Wasn't that fun? I love proof by contradiction.
It was easy.
We showed it can be, right? We showed how ridiculous this is. And so we said it's a contradiction. It's absurd, right? So that means what we assume must be false. Well, if what we assume is false, then the opposite must be true. Right?
There's gotta be a catch. Like it can't
No,
be this
it has to be a fake date.
Normally when we do proofs, we use deductive reasoning. Right? We just get to the point where it proves exactly what they wanted us to have, right? This is called proof by contradiction. There's also inductive reasoning, which we haven't gotten to this year. But it's also, both those techniques are very powerful. All right, 2.
322.
Prove the sum of 2 numbers, or 2 even numbers, is always even. So think of 2 even numbers, right? Do fractions count as even or odd? No, they don't, right? Only whole numbers that can be positive or negative can be even or odd. So think of 2 even numbers. They can even be negative if you want. Add them up. Do they add up to an even number?
What?
Yes.
Take 2 even numbers and add them together.
Yes.
Thank you for being here. All right, so here are 2 numbers, and they exist in set Z. Well, set Z, just so you know, is the integer set. If you had me for algebra, you would know this because I drill it into your heads. Integers are negative and positive whole numbers. So anything from negative infinity to negative 3, 2, negative 1, 0, 1, 2, 3, etc., right? That's all that is, just so you know. Okay? So any of those numbers you can choose for A and B. And I said we're going to prove that double A plus double B is even. Now, why did I choose to write that instead of A or B? Well, if you look, if I can choose any of these numbers, are some of these numbers not even? Right? So what I did is I said, once you choose one of these numbers and you double it, that guarantees an even number. And here's why. Here's how we define even. If a number can be divided by 2 and the answer is a whole number, right, then it's an even number. So like 4, when you divide it by 2, you get 2, which is a whole number, right? 4 divides by 2 evenly, so we call it even. That's why it's called even, dividing evenly, right? If you take 5, right, and you divide it by 2, do you get a whole number? No, you get a fraction, right? 5 over 2, 2.5, right? So what we're going to do is we're going to prove that this has to be even, 2 even numbers, okay? And we know that 2a is even. We know 2a is even because if I divide 2a by 2, what do I get?
2. I mean,
A, right? And that's a whole number, right? Same thing with b. 2b is definitely even because if I divide 2b by 2, I get b, and b was a whole number, right? We are going to assume the opposite, though. So we're going to give the answer. We're going to call the answer C, right? And we're going to assume that C is negative. I'm sorry, not negative. Odd. Odd. Sorry, that's the opposite of even. Odd. Odd. All right. So here's what I'm going to do. First thing is I'm going to pull out a 2 from both. Remember that as a valid strategy. They just didn't teach you about it in middle school because you weren't mature enough to handle it. It's just reverse distribution, which makes sense when you think about it. Then I'm going to divide both sides by 2. Cool? So now I'm here, and now there are 2 cases to consider. Case 1, c over 2 is not an integer, meaning that after I divide c by 2, I get a fraction, right? These are integers, right? It's every number except the fraction. So if I say not an integer, I mean it's a fraction. So c over 2 becomes a fraction. So if c were 5, right, then it would be 5 over 2, which would be a fraction. And this is absurd, and here's why. A and B are both integers. Can you ever add 2 integers together and get a fraction? No, right? 3 and 4 you add together, you get 1. Negative 5 and 2 you add together and get negative 3. Will you ever get a fraction? No. Any of these numbers added together will not produce a fraction. So if c over 2 is not an integer, meaning it's not one of these, it means it's a fraction, right? If that's a fraction, because it can't be simplified, then that's absurd because you can't ever have 2 numbers add together to get a fraction, right? 2 regular numbers, 2 integers. So that's absurd. So we write contradiction. Case 2, well, if it's not an integer for one case, what's the other case? If it is an integer, right? That covers everything, right? You either are or you ain't. That's right. So what if c over 2 is an integer? Well, if this comes out to negative 3 or negative 2 or negative 1 or 0, whatever, right, after we divide by 2, what must have c been? No. Even, right? If you can divide c by 2 and you get an integer, isn't that the definition of even, right? So that would mean, that would imply that c is even. That's what that arrow means, is imply. Remember back to the beginning of the year. Which is a contradiction. So we have 2 possible answers. Either it's an integer or it's not, and both don't make any sense. So our assumption must have been wrong, right? Our assumption that c was odd. So I'm going to say, therefore, our assumption was false. And if our assumption was false, the opposite must be true. So therefore, 2a plus 2b is even. There's a shorter way to prove this. I could have stopped right here and forgot about the c, and I could have asked you, can I divide this by 2? And what do I get? A plus b. And a plus b, if they add together, are going to be a whole number, right? So that must have been even, right? But I thought this was more fun.
Wait, what's the lightning bolt again?
Contradiction. Absurd. Erroneous.
Why is it a lightning bolt?
It's just a symbol some people use. Yeah. You like it? Good. Good. I was hoping you would. Made it up just for you. All right, that's proof by contradiction. So let's go back and relearn proof by contradiction for Ceva's theorem's converse. Let me grab that. So back to the packet.
I think I didn't even have it. I got myself.
Back to the packet. Oh, and also, yesterday I found out that the back of your packet has a mistake in it. I don't know if I made more copies though. Let me see if I did. The last page in your packet has a mistake. I don't think I made more copies. We're not going to worry about it. We'll take care of it later. Wait. Oh, I did make more copies. They're right here. Check the last page in your packet. Page 8. It probably doesn't look like this. Look closely. There are differences. This C means.
Oh, yeah, the water, right?
Yeah. What happened was when I was making it, my computer crashed, and I thought it saved the whole thing. And so when I went back and looked at it, it looked right?
A.
Yeah, but it turned out that it had saved in the middle and not after I fixed it. And so when I went to print it. They printed the halfway done version.
I don't know about that.
I copied and pasted the template and didn't change the stuff out.
Bailey, we're doing that right now.
Oh,
So here's what's correct version. We won't be doing today.
What did you say?
Their equation.
I'll pass around a stapler. We'll finish this up on Monday.
I already have this paper.
No, you don't.
Dude, I can't wait.
Guys, she can't handle this. She has to
I can't
have
wait to buy
silence to
So
be
what do
correct.
I do?
Why is it still snowing?
No, so she can hear what's going on. Shut up, Zen.
No one
Do
cares.
I add-
So, the last page is wrong in your packet. It has errors on it. So take it out and replace it with the new one.
Is this the new one we replaced?
Yes. Some of you, not in this class, but some of you can handle like the talking and being able to pay attention, but this class just, oh my God, cannot.
It's supposed to snow till 10.
Zed, no one cares.
Shut up.
Way too long.
You're the problem.
Yikes.
That's wrong.
He's not the
We don't
problem.
turn anything into
No. Next week is when we have a quiz. We only turn stuff in when we have a
I've been
quiz.
trying really hard not to lose these.
That's great. I'm proud of you. Oh my God. Your parents are worried because I don't give enough homework that you won't be ready for college, when in reality it's really just your organization skills that
You know
suck.
how often my
And I help with that a lot.
She lost her car.
I can't.
She lost
Yikes.
her car once.
Just smack her down, Hannah.
No, I have
Do it. Do it, Hannah.
I don't have that in me.
She
Okay.
also lost
I'm afraid of
her
Bailey's
car at a
elbows.
gas station.
That's why I don't tell her to be quiet, because I'm afraid she'll hurt me.
Me too.
All right.
Who is he talking
You.
about? Oh.
There's a lot of snow.
Yep. Zed, sit down. No one cares.
Hey, my mom lost her car once.
No one cares.
I also lost.
Slide out.
I remember when I used to teach kindergarten and kids would just tell me things that I don't care about. And now I teach high school and they tell me things I don't care about.
And then you follow it.
Like no one asked
I decided
about your trip to
yesterday-
Disney World.
You know what?
You care about this.
You want to be a teacher?
No, I decided yesterday that I'm not going to.
It's probably a good
You
choice.
ever been to Disney World? Are we doing that right now?
That's cool.
Yep.
But
We did this yesterday.
Wait, where's the
All right, everybody shut up so you can hear me. My voice is not as strong as usual, and you guys are dumber than usual. So listen up. We already did this one. This is page 5. So you're not going to write this down.
Okay.
Remember yesterday? You're not going to write this down.
then why do you give it?
Okay? We're going over it again. There are a few of you in here that agree with me and want to kill your classmates, and I understand. They are drinking big dummy juice today. All right. You don't have to die, you just have to be quiet. All right. Because we've proven that not only can you not learn while talking, but your neighbors can't either, and that's when I really get mad. Because you can screw up your own education, but don't screw up anybody else's. All right.
I need to see.
So, to prove Ceva's converse,
Stop distracting me.
to prove Ceva's converse, we're going to use proof by contradiction. It is the easiest way to prove it. We did this yesterday. So what we're doing is we're taking this, where it says the Cevians are concurrent, and we're going to assume that they're not concurrent, right? So assume AE, BF, and CD are not concurrent. Now, what this allows us to say is, look, if I've got 3 lines that are not concurrent, if you pick 2 of them at a time, unless they're perfectly parallel, right? 2 of them at a time will be concurrent, right? So if I choose 2 of them, there should be a 3rd line that would be concurrent with the other 3, or the other 2. So if they're not concurrent, that's fine. I'm going to find the line that does make them all concurrent, right? At least 2 of the ones that they gave us. So we're going to assume that CD is the one that's just off, and we're going to try and intersect with FB, and AE. So I'm going to draw this line, and it's going to look ridiculous. Again, we're trying to prove absurdity here, so it will look a little weird. I'm going to draw a line from vertex C to the opposite side. I'm going to draw on a Cevian. And I'm going to claim that if CD isn't concurrent, if CD isn't intersecting all these lines, even though it looks like it is, right? Then if CD isn't, the line that I'm drawing is going to be. So I'm going to say let CX exist and let ADXB exist. Now remember, if two lines share a point, that means that's the point they intersect at, right? And CX, AE, and BF are concurrent. So that's what I'm assuming. That if CD isn't concurrent, then I'm drawing the line that is concurrent with the other three, whatever that line is. Now, in order for me to draw it on the diagram, I had to draw it really weirdly, right? But there it is. Well, we know from Ceva's theorem, so by Ceva's theorem, that if I have three concurrent Cevians, right, and I do according to my assumption, right, then I should be able to use Ceva's theorem and say that this length right here from to here should be proportional to C to D and E to F. Are you following me with that? Is that where I lost you? Hello. Okay. So if these three are concurrent, ladies, if these three are concurrent, right, which I'm assuming that this, and this are, then I should be able to use Ceva's theorem, right? That says if I have three concurrent Cevians, right, then I get whatever this is divided by this equals this over this equals this over this. So AX over XB should equal C over D. Sorry, not equal, it's times. I've done this every single time. C over D times E over F. And it should equal what? Ceva's theorem. What should it equal? 1. Cool? Now, by the same logic, I know from here that A over B times C over D times E over F equals 1. So I'm going to write that down. Now, when I write A over B, instead of writing A, I'm going to write AD. Does everybody see that that's the same? Cool? And instead of writing B, I'm going to write BD. We cool with that? So I'm going to write AD over BD times C over D times E over F equals 1. Now this, just so you know, you don't need to write this. But that was given to me, right? All I did was replace AD and BD with A and B, right? Cool. Now, my logic is, if this equals 1 by my assumption, and this equals 1 by the given, don't these two equal each other, right? So that means AX over XB. I'm going to write BX. Doesn't matter. Times CD times EF should equal AD over BD times C over D times E over F. You follow me with that logic? All right. Now, through the magic of math, if I divide both sides by EF, what happens?
1.
They both become 1, right? Anything divided by itself is 1. If I divide both sides by C over D, what happens?
1.
And so therefore, everything times 1, right, is just AX over BX. And that'll equal AD over BD. Now, here's the part where I say this is absurd. AX over BX is a certain ratio, right? And it should be the same ratio as AD over BD. How do I cut a line into two ratios that are equal using different points? Let me say it again. If I have a line and I want to cut it into like 1/3 and 2/3, right? Remember this is kind of like section formula? If I want to cut it into 1/3 and 2/3, how can I do that with 1/3 being on the left and 2/3 being on the right using a different point where I cut? How could this point also cut it into 1/3 and 2/3? It can't, right? The point that cuts a line into a certain ratio is non-variant, meaning it doesn't change, right? That point is always the same for that line. If you want to cut a line in half, right, it's always the same point that you go to cut it in half, right, the midpoint. So how can I have congruent ratios that are also different lengths? That doesn't make sense. AD is a different length than AX. Unless what? AD and AX were the same, right? So what if D and X were the same point? So in order for this to be true, D and X would have to be the same point, which we assumed earlier wasn't the case. So now D and X will be the same point. That must be true. D and X must have been the same. This CX line must have been the same as CD. And CX was concurrent, right? So if CX and CD are the same line, CD is concurrent. So this is absurd. Therefore, D and X are the same point. And you can kind of see it a little bit algebraically. It's not really algebra, but if you look, AX over BX equals AD over BD. Those are both going to have to be D's, right? Therefore, AE, BF, and CD are concurrent. And we win. I explored a scenario where they weren't concurrent but still satisfied this, right? And it didn't work out. I would have to have two different points that had the same ratio. And that doesn't make any sense. You can't cut a board in two different spots and expect to get the same amount of board, right? So they must be the same. And if they're the same, then it was concurrent to begin with. So Ceva's theorem works forward and backwards. We're going to use the reverse Ceva's theorem converse, that if this is true, then they must be concurrent, to prove things that like angle bisectors are concurrent. So on Monday, after we learn one more theorem, we're going to prove that these lines are always concurrent. Why? Because they're Cevians, aren't they? Right? And Cevians always divide up into this. And we know if they're Cevians and they're concurrent, right? Or if we have this ratio equaling 1, then that implies by Ceva's theorem's converse that they're concurrent. This will be true for all angle bisectors. Now we have to prove that this relationship exists, right? For any set of angle bisectors. And we're going to do that with the theorem we learn next, which is going to be called the triangle angle bisector theorem. So when you have a triangle and you have one angle that's bisected, this crazy property happens. These sides are proportional to A over B, which right now, there's not enough information to prove that. You're not going to prove these two triangles similar, so you're not going to get that. What has to happen is we have to draw them one more triangle. I'll see you on Monday. Please come with your A game on Monday. I need to catch you up to the rest of the classes. Oh, yeah. About a class. No, you don't, but you will.
Can I come in during homeroom?
Please.